for my own good. And that's what this algorithm is doing. So we are observing in real time, this simple freaking algorithm is delaying gratification to get a better outcome in the long run. Are you as floored with how cool that is as I am?
Not even a little bit.
Let me say it again. Maybe I just didn't pit. No. Okay. Why not? Why not? Why are we not compelled? This is Philosophy, Programs, and Prompts, a podcast where two real humans sort out whether algorithms are doing more than meets the eye. I'm Casey Hart.
I'm Carl Brown.
And those starting lines are supposed to be like pithy and jokey, and I was trying to do a play on sort out, but that's not going to make sense to you if you're watching this for the first time. So audience members, when you rewatch this video, because you should be watching all of these twice,
at least,
then you'll think that that's super, super clever because of all these sorting algorithm stuff that we're going to talk about. Today, we are going to do the thing that like maybe I was most excited about when you and I first talked together about collaborating on either like YouTube videos, and then this podcast became a thing. And that is to talk about Mike Levin. So I know you're at least a little familiar. I threw some stuff at you in advance of this video, so it wouldn't be coming totally out of left field. But just to give everybody some background here, what I got excited about this or learned about this was because my dad told me I needed to watch this Curt Jaimungal podcast video, and we'll drop that below in the description as well. He's a YouTuber who has on academics, and they talk about a bunch of different things, like Lex Fridman-ish is the vibe that I get from him. And in this particular video, he had on this guy, Michael Levin, and another guy, Anil Seth, I think, and they were talking about what minds were and this crazy idea that Mike had that you could get free compute. And you could see that you could get free compute because these algorithms, like sorting algorithms, were doing things that nobody had ever seen possible. And it sounds crazy, I know, but it's amazing. And I watched that video the first time. I was like, this is terrible. Like, this is obviously garbage. And in so saying, I offended my father, who recommended that I watch this video. And fair enough, I was probably a little too mean. And what proceeded from that was me listening to hours of his content, reading, and many of those videos, listening to them 5, 6, 7 times over. Probably some sort of mental disorder on my part to do those sorts of things, reading a bunch of his articles. And I now feel like I understand his stuff well enough. But I didn't feel like I understood it well enough from a computer science perspective. And I was like, if only I could convince some computer scientist, some programmer to sit down with me and talk for extended periods of time. And you are that victim, Carl. So are you ready to talk about Mike Levin and his panpsychism today?
Yeah. So I ran into this, I don't know, a month or two ago, maybe. There was an article in Forbes called something inane like The Secret Life of Algorithms, or something to that effect. I'll track that article down and I'll stick it in the show notes too. And reading through that, I was like, okay, this is obviously written by someone who doesn't understand the tech and didn't spend any time or effort pushing back on what they were presented, and was just kind of parroting things the way that I get irritated when reporters just tend to, rewrite press releases and release them as if they were fact. So that was, I haven't had nearly as much experience with his stuff as you have, but that was my kind of introduction to the idea. And when you sent me the video over, I was like, okay, this sounds really familiar. And I went and looked at Obsidian, which is the notebook app, markdown app that I use to keep a bunch of stuff when I'm prepping. I like throw a bunch of stuff into ideas for videos I'm going to make and that kind of thing. And I went and looked at Obsidian. I was like, search for Levin, and was like, oh, okay, yeah, okay, I remember this article. So I have a cursory understanding of kind of where a reporter said he was coming from, at least.
Beautiful. All right. Well, and as I think will happen over the course of this video, everybody, you might want to watch it a little bit, because I want to see how angry Carl gets as we go. Because my theory is he's going to get more upset, but maybe not. We'll see. So who's Mike Levin? Dr. Mike Levin. I think he's just, I've had personal correspondence with him, and he's just called himself Mike in the chat. And so I have no problem. And plus, we're PhD people that refer to each other by our first name, so it's not disrespectful. All right. Here's the Wikipedia description of his bio. Michael Levin is an American developmental and synthetic biologist. He is a professor of biomedical engineering at the Vannevar Bush Distinguished Professor of Biology at Tufts University, where he's the director of the Allen Discovery Center and the Tufts Center for Regenerative and Developmental Biology. That's a mouthful. He is also co-director of the Institute for Computationally Designed Organisms with Josh Bongard. And so he's a biologist who runs a bunch of experiments, and he especially likes stuff where we're like mixing cells from different creatures and seeing how they behave, like putting the damaged organ in a petri dish and then like putting nanobots in there and seeing like, will they tear up the thing? Will they heal it? Which has all sorts of like pretty cool applications. Like when you're thinking sci-fi, like, you know, Darth Vader is in a pod and like being healed up in this sort of fluid. Like it feels like that's the kind of stuff that Mike Levin wants to be building. And he is incredibly prolific, bunch of publications out there. So we're going to talk about one thing in particular from him. But I think before we get into that stuff, I want to introduce a couple of different like philosophical / computer science / sciencey terms that we're going to be leveraging a lot throughout the discussion. So the first of those is substrate independence. What does that mean to you, Carl?
So my physics brain says basically you've got one layer of atoms that's been laid on top of another layer of atoms, and they don't interact with each other. So like in a semiconductor kind of fashion. But I don't know if that's actually where you're going with this or not.
Oh, good. Yeah, not here. So what I have in mind for substrate independence and how that's going to come up in this conversation is, does it matter what kind of stuff is doing the thing? So in the case of minds, substrate independence or substrate dependence might be the question of like, okay, the reason this thing can be a mind, as I squeeze my head, is that I'm made up of the right sort of biological stuff. But we could, and we've talked about this a little bit on the channel before, right? If AI is possible to like that to make an artificial person, then it's got to be something like silicon or some other substrate could realize personhood. But if you have a substrate dependent view, you might think that only biological stuff is the kind of stuff that can give rise to personhood. But this is the question. So can and in particular for mental contents, if we think what's going on in thinking is just a bunch of algorithms being realized, and you could do that with brass cogs, you could do that with silicon, you could do that with biological cells. The world's your oyster.
In a computer science context, we tend to call those layers. So for example, there's this thing called the OSI model, which is the way networks are laid out. And you've got a physical layer, which is basically exactly how the wires plug into each other and how the electrical signals move along the wires. And then there's the data link layer, and then there's the transport layer, or no, the internet layer and the transport layer, and so on and so forth up there. So it's the same kind of concept. Although in computer science, the explicit goal is for each level or each layer to be deliberately and explicitly independent of all the layers underneath it, to make it a lot easier to reason about. But yeah, it's the same kind of idea, I think.
Good. And the kind of stuff that comes up with substrate independence a lot is that there's sort of a sense in which anthropocentrism is bad. We're like, oh, humans are just better than everything else. He was like, look, if something else could think the way that we do and could make moral decisions the way that we do, et cetera, like that's the sort of stuff that counts. And similarly, if they can compute the way that we do, then they're thinking, and we don't have to say, oh, you're not special because you don't have a brain, right? Like we're trying to avoid that. At least that's going to be the discussion. And there are some others who are pushing back on this more recently and saying like, no, actually the stuff we're made up of is like pretty important, and like mental properties depend on that. All right. Second preliminary, the scientific method and open-mindedness. And this is not, and like, I don't think this should surprise anybody here, right? In the scientific method, we make hypotheses and then we run experiments and we test those hypotheses. And sometimes we can reject those hypotheses and sometimes we can fail to reject them. And the general idea here is that good science says that any hypothesis is fair game, right? So if I come to you and I'd be like, I think that your shirt is sentient, like that's a fine hypothesis. Now I have to be able to come up with an experiment that will test that, and we'll see what happens. But there's no hypothesis that is just off limits. Fair enough. All right, and I like that. Like this is a thing. these are all things that I think are sort of central to the way that Mike Levin views the world, and like some of them I really do appreciate.
Yeah. Although one thing I want to say about that, that we'll come back to later, is it's very important in the scientific method to create the hypothesis and then do the experiment and then decide whether or not that reinforces the hypothesis or not. If you do the experiment and then you look at the results of the experiment and then you say, oh, okay, from that, I'm going to pretend that I had the hypothesis of XYZ, then that's not really science. That's, projecting.
Absolutely. Or we do p-hacking and stuff like that. Yeah, take any body of evidence you like. We'll find some correlations, and we can pretend like that's telling us something meaningful. But there are always going to be unlikely correlations in any data set that you pick once you get sizable enough. Okay, cool. And then the next one is Platonism and like the Platonic space. So this goes back to Plato, named after that. Do you have any familiarity with like the Platonic realm, those sorts of things?
I guess not. I'm familiar with some of Plato's writing, mostly in the political sense, though.
Good. So, and for it's all intertwined to some extent, but the Platonic realm, right? When there are a bunch of problems that we're trying to solve here in metaphysics, but one of them is to say like, okay, my sweatshirt is blue, right? And my shirt is blue, and like you've got some blue stuff in the background, and for those of you who are listening, if you look around, you'll see some blue things around. In virtue of what are they all blue, right? They're different objects. So like, what is the thing that they all have in common? One way to think about it is that there's some universal blueness, and they all are similar to that universal. They all sort of partake in it. But then in Plato's view, we have like this realm, like where is the universal? Like, is the universal like floating up in the sky or something like that? No, it's in Platonic space. Like where they're the Platonic ideals of things. And this is the kind of stuff where metaphysics is wonderful. It sounds super weird, and I agree with you that it sounds super weird. But it turns out that you're going to have to say something really weird about metaphysics. Like either you have to say that all these objects are just their own thing, and it's weird convention by which we say that they all have the same thing in common, blues. Like that can't be it. But like what is the thing that binds these together? And we could go down many rabbit holes here. But Platonic space you can think of as almost like a spiritual realm, like another realm that's just not part of the physical world. And this space does some important explanatory work for us. Maybe it's where our minds live. Like we have physical space, and then minds are up in the Platonic realm. And that's actually the kind of picture that Mike Levin is going to advance here when we talk about Platonism later.
So I'm assuming this applies to like more abstract concepts like love or that kind of thing. Because when you bring up blue as an example, right? I'm a physicist by training, right? And so I'm going to be like, okay, well, that means the light coming off of it is going to be between this particular and this particular number of nanometers, which is not a thing that Plato would have understood, but but I think that has a much more concrete kind of explanation than the idea of like, what do the love I have for my wife and the love I have for my daughter have in common, right? Kind of thing.
It's interesting that you go to the wavelengths, which I think is a totally reasonable place to go there. But then we're talking like more mathematical stuff as well, and like that's where Plato thinks like mathematical entities reside in the Platonic space as well. Like that has a tradition going through famous mathematicians who, when they talk about math, like you have this distinction between whether math is like just purely definitional or whether it's discovered by people. And some who think that it's discovered think that like I'm hiking the mountains in Platonic space and like looking over these natural features and seeing that this is a prime number and like that exists independent because 13 is out there. Now, all sorts of different views here, but the important concept is that when we're talking about a Platonic view or a Platonism, and not just Platonic in terms of like our friendship being strictly Platonic, but like a Platonism of that there's this other realm that's somehow detached or different from the material, and that also it's usually used for some sort of like important explanatory feature, like why is the material world and why are things the way that they are. It's part of some holistic picture.
Okay, that makes sense.
Okay. And then also, while I'm doing gestures on two different levels, let's talk about levels of selection and supervenience. And so an example here might be something like, let's say we can think of a simple toy, right? One of those toys where you've got a cube and a triangular prism and a cylinder, and then I've got a board that's got some shaped holes in it that you can slide those things through, right? And I could ask for an explanation for like, why did the cylinder go like fit through that hole? And one explanation could be something as simple as like it's cylindrically shaped. Okay. And that seems valuable enough. Like, all right, it's got a radius of 2 inches and same for the shaped hole in the board in this kid's toy that we're playing with. But I could also say, no, that's wrong. Like, actually, the fundamental thing that's going on here is at the like atomic and subatomic levels, right? Like, I see where all of the matter is. Like, we've got protons and electrons, and these things are in space. And the reason why that quote unquote cylindrical piece fit through is because it was such that none of its protons and electrons collided with in such and such a way the protons and electrons in the shape of the board that it went through. Right. So instead of giving you a like macro level description about this is a cylinder, I want to give you a micro level description of this is where all of the particles are that are sort of loosely joined together in that macro object that you're talking about. And we could get in a fight about this where I say like, okay, my explanation is better because it's a micro explanation, and that is more important than this macro explanation.
And I could say, well, that micro explanation would be the same for any shape you're talking about, right? Because, if these atoms are not running into the atoms of the thing that it's going through, then that means it fits, but that's independent of shape. And so a much better explanation is to talk about the cylinder and the circular shaped hole that the cylinder goes through, because that's specific to the particular object that we're talking about, as opposed to other objects on that same toy, the star-shaped one or the square-shaped one, whereas your explanation is going to be the same for all of them, and so mine is more specific to the actual thing that we're dealing with.
Beautiful. And there's all sorts of ways that we could go with this, but the things I want to take away here are, one, that we could talk about explanations at different levels. Two, we could say that certain facts about the macro level supervene, and this is that supervenience word, on facts at the micro level, which is just to say that if we changed enough of the micro level things, we could change the macro level things. And if we in order to change the macro level things, we would have to change some of the micro level things. Another parallel that gets used here a lot is the difference between the screen that you're looking at and the pixels on that screen, right? So I might describe the image that I'm seeing on my monitor right now based on the shapes that I see on the monitor, but those shapes are built up out of individual pixels, say, right? And we can talk about how those pixels serve as like a supervenience base for the type of image that I'm seeing. If you change my image, you're going to have to change the pixels that are there. And then there's all sorts of other things that we could talk about, what makes a good explanation or a bad explanation, and that would take us far longer than we're going to get any traction on in this particular podcast. But I just want to introduce that because that's going to be an important thing going forward for what Mike is going to say about things, which is like if you have physicists who are looking at a problem or computer scientists who are looking at a problem, they're giving you one view and one level of selection and explanation. But it's possible to like look at different levels of explanation, and they might be equally valid or maybe more valuable, as you're pointing out. Like in different contexts, I want an explanation at a different level that might just be more relevant to the phenomena. Okay, so those are 4 things. We've got substrate independence. We've got let's be open-minded in our hypotheses. We've got this Platonic realm as like a thing we might want to think about, and that there are different levels of selection. And the last thing that I want to say here, I just want to make sure that I'm being nice enough, because sometimes I'm a mean guy. And I like have a lot of appreciation for some of the ideas that Mike Levin has. And these 4 in particular, I think are important things that he brings up and like helps educate people about and think about. And I also say that when I had issues with, okay, how do I understand this stuff? I emailed the guy and he emailed me back quickly. And with like some thoughtful comments and suggested other things for me to read, and didn't know me from from Joe, whatever the expression is. He sent me an email, so I appreciate all that stuff. Now I feel like I can go and be really mean to him for the rest of the episode. That's how this works, right? I think. Okay, cool. Let's get into the details. So here's the story. This is the sorting algorithm example, and the way it works is we start out with a couple of different sorting algorithms, and I could try and define them, but Carl, you're going to be way better. Like, what is a sorting algorithm? Can you give me a couple of the popular ones to help people understand?
Yeah, so the idea of sorting is basically, I mean, we've all done this. We've all put things in alphabetical order, or we've all, taken a deck of cards and like put them in order to make sure that none of the cards were missing, or that kind of thing. It's basically some way of taking a bunch of things that are chaotic and that are, in some kind of random order, and putting them in a specific order so that you can do something that's more, more interesting with them, or to make some, to make some judgment about them that's a lot easier to do when they're ordered than they are when they're just kind of thrown together. A couple of the primary sorting algorithm I think we're going to be talking about today is a really, really simple one, which is called a bubble sort. And basically all a bubble sort is a thing that you go through and each element is compared to its neighbor. And whichever, if the
and for simplicity, let's just say they're all numbers in a list that we're trying to order.
Yeah. So if if we're trying to sort from least to greatest, then basically you look at these two numbers that are next to each other, and if the one on the left side, the one on the side that should be lower, is actually higher than the one that's on the other side, then you swap the two, and you make one pass through and you swap all the neighbors that are wrong, and then you go through and you make another pass and you make another pass, and eventually what will happen is the longest or highest number will get bubbled all the way to the right, or all the way to the end that's supposed to be the highest number. And the next one and the next one, and that's kind of the way that it'll go. It's not a particularly efficient algorithm. There are lots. Quicksort is a much more efficient algorithm that we generally use in more real kinds of contexts because it's a lot faster. But the great thing about bubble sort is it's really easy to understand what it's doing, which is why it's a thing that we teach to, beginning programmers, because it's really easy to kind of do it in your head so that you can see whether your code is doing what your code is supposed to be doing or not.
And you also learn a lot, if I understand this right, about, okay, there are a bunch of different algorithms that accomplish the same goal of sorting this list by the end. And this bubble sort, like you said, it can be super slow because if we have, is the slowest version if the list is totally inverted? So if it's greatest to least, and then we have to go through, then like you're going to have to do a bunch of passes to get that to resort. But alternatively, we could do one where we just go through the whole list and we find whatever the smallest number is, right? So you start by keeping the first element, then you check the second element. Is that smaller? If so, you take that one and you keep going till you find the smallest element. And now you know that's the first element in my list by the time I'm done, right? And then there's finitely, like, this is going to take me n times for a list of size n, but I know how I'm going to get through it, right? This is the other idea, is that you could teach people a bunch of different facts about how long it's going to take to run your program to quiescence.
Yeah, and over time, there are lots of algorithms that we deal with in computer science and in software engineering that have, specific, this is going to take, so long based on how large the number of elements are. And a lot of times in computer interviews, we want to talk to people about, okay, so, is this O(n)? Is this O(n) squared? Is this, a function of the logarithm of the number of elements, that kind of thing? Which of these are better or worse in a particular context, that kind of thing. Bubble sort, like I said, is not a very efficient algorithm, but it's really simple to understand, which makes it valuable in a teaching context, although not really in an engineering one.
Cool. So Mike says, great, we've got these sorting algorithms. We're going to take a couple of these sorting algorithms and we're just going to sort some lists. And the reason he picks a sorting algorithm that he states over and over again is that this is super simple and it's well understood. So if we can find weird stuff going on with like this simple, explicable algorithm, seemingly explicable algorithm, then if that turns out to be weird, that should just, turn the world on its axis, right? That's going to be crazy if we find stuff here that we didn't expect before. And so the first thing that he does to perturb this situation is he freezes an element, which he says, okay, we're sorting this list, but what if we make one number? Now, it's the first on different tellings. Yeah.
I mean, the first thing he does, the first thing he does is he tries to give the individual elements agency. So instead of having a large orchestrator level on the top that basically loops through all of the elements and makes some changes to them, He basically tries to, keeping the same rules, which we'll talk about later, let each element behave in its own way of making its own decision about what it's going to do based on what it thinks the right thing to do is based on the rules it's supposed to be behaving against.
Good. And this is in line with, so it's interesting that you bring that up as the first thing, because he's, having watched about 50 different times where he tells this story, sometimes he brings in the broken elements first and sometimes he brings this other one. The thing you're pointing to here, I think it was like, it's really, it fits right in line with the kind of stuff that he does with biology, right? Where he's interested in, okay, here's how whole organisms work, but also like the different cells and parts of the body may do things differently, right? Like I'm not thinking about what my white blood cells are doing right now.
Right.
And so his idea was, okay, what if we take, or his grad student's idea, whatever, I don't want to attribute this to the wrong person, but instead of doing this top-down strategy where we say, all you in this list do the bubble sort, right? Where you just execute the algorithm over it. Instead, I tell element 1, I want you to switch with your neighbor to the right if they're bigger than you. Also, element 2, I want you to switch with your neighbor to the right if if you're bigger than that. Like, so you go through, and then you have like this distributed method of executing the algorithm. And what he wants to see is like, okay, is this more or less efficient? How does this function? And he runs it. And again, same thing happens more or less, right? We end up with a sorted list. And I think there's plenty to be said here. And I mean, I guess I will just ask this to you quickly. Like, that might be interesting, right? Is just seeing how the efficiency differs in a top-down versus bottom-up strategy for sorting. You might care about whether that's faster or slower.
I mean, maybe. The problem is we're now in two fundamentally different kinds of substrate. I mean, of layers, right? When you do programming for a while, right, and you do software engineering and you do software engineering at large levels, what you find very quickly is that having a lot of things that are going independently of each other, right, leads to a lot of weird kinds of opportunities for race conditions and things to happen in the wrong order, and weird kinds of side effects that happen. And so when you take something that's very simple and you make it into a bunch of asynchronous, time-independent versions of that are all happening kind of simultaneously, it's a very, very different kind of phenomenon in a computer science sense. In a biological sense, that's always the case, right? A cell always has some amount of, call it motivation or, however anthropomorphic you want to be. But in a software engineering sense, in software, that's not the case, right? And so when you go and you change from, okay, I'm going to do this for loop and I'm going to walk through every element one at a time, to each element is running its own little subroutines, that's a very fundamental change in a software kind of sense, in a way that kind of change isn't going to you're not fundamentally changing it when you're talking about moving from the level of an organ to the level of cells in an organism, because those two things are already independent of each other. That's not at all true in a software.
Okay. And the other thing that what you're saying here makes me think about, right? Like the initial assumption, again, was we're doing sorting algorithms because they are incredibly simple. And like what he's going to say over and over again is it's 6 lines of code or something like that. Can you give me a sense of like how much more complicated is the code going to look from the initial bubble sort to the bubble sort that's enacted by the individual entities in the list?
So in the paper that I read, there is no code. And so I can give you I can give you a bunch of different ways, because he didn't actually specify how he implemented it.
Which is already a red flag.
Which is already a red flag,
no
yes.
code. Yeah.
But one of the things that I read is that basically that each element has the ability to decide for itself when it wants to switch, and whether it wants to switch to the left, whether it wants to examine its neighbor on the left or its neighbor on the right. And if that's what we're talking about, we're in at least an order of magnitude, if not 2 or 3 orders of magnitude more code than the 6 lines of code it would take to just run through everything in a for loop once or twice.
Okay, good. So worth bearing in mind that any traction we want from simplicity here is already tenuous at best,
Oh yeah.
right? Because it's no longer as simple a code, and it's going to get more complicated in just a second. Okay, so we've got these two things that we're running. We just like simple sorts that can be bubble sort or insertion sort or whatever. We can look at these sorts. Then we have these sorts realized on the more like individual, quote unquote, cell level, where each number gets its own algorithm that it's executing rather than the top down algorithm. And then the next thing that he wants to do, and this is where we really get into some behavioral and mind kinds of talk. And that's the thing that I was mentioning earlier, which is we take a cell and we break it. We make it so that it can't be sorted. It's not allowed to move. And then we see what happens. And the observation here, I think, and you can correct me on this because you probably are already more informed when you were reading the paper about it, but I think if you did the top-down sort, it would just terminate, right? You would get some sort of error because it needs to switch two elements at some point, and they can't switch. And so that would just like throw an error in the code or something, and it would stop probably.
I mean, it might. He actually talked about this in one of the videos I think that I watched, where basically when you're doing a sort in a computer sense, you don't check generally to say, when you say swap these two array elements, right? You generally then don't read them back in and make sure they're in the order that you thought they would be.
Okay.
Right.
In which case, you tell it to do the thing, whether it happens or not, it's moving on to the next line.
Right. And so he was one of the things he was talking about was basically, what happens in a world where you make the mechanism not as foolproof as the array, as the straightforward algorithm would expect it to be, right? The actual the actual what would happen is largely a function of like what kind of array you're using and what kind of language you're using, right? In some sense, and also how you decided to break the algorithm, how you decided to make that element stay in its same place, right? So under some languages, you would say swap these two. It wouldn't happen, and you just go to the next one and say, okay, swap those two. Okay, how big are these? Okay, swap those two. And two of them would stay where they were, and you wouldn't really realize it. You would just keep going to the next thing. And then you would come back and you wouldn't even realize that you had already tried to swap those things and they didn't swap. And you just keep going over them and over them and over them because you're not keeping track of that. You're not thinking of that, right? That's the 6-line of code version. Yeah. There's also a world where the array that you're using, when you call the function that says, hey, swap these two things, that swap function will throw an error back at you and say, hey, I couldn't swap these things for, long stack trace reason here. And at that point, depending on the language that you're in, a lot of times what will happen is either you decided to handle the case where the swapping didn't happen correctly and you've got an error set of code that deals with that, or it will crash the whole program because an exception got thrown that you weren't expecting. And so, that's if you've got error checking in there, you've already blown through the idea that you've got a 6-line set of code because, there's no way you're going to do error checking in 6 lines. So, depending
You're just not as efficient as I am in writing code.
Yeah, there you go. Well, I mean, that's part of my whole Internet of Bugs thing, right? The kinds of bugs that you get on the internet that make things hard for everybody are the ones where you tried to do everything in very small lines of code and you didn't spend a lot of time trying to figure out what your error states were going to be. And then an error happens because that happens on the internet a lot, right? A packet doesn't show up when you expected this packet to show up, or it shows up out of order, or some, malicious actor tried to get you to get your environment to behave in a way that it's not supposed to behave to try to get your code to do something stupid. And so if you don't have a lot of good error handling, that causes problems, not just for you, but for all of the people around you, because your machine can get turned into a launching pad to make attacks on, the other things on your network. So, the efficiency is not a thing you want in error handling. You want a lot of robustness in error handling. Efficiency can be great in the happy path.
Good. Okay. So now I'm gonna channel Mike here, and I'm gonna tell you and the audience something incredible. So we have the simple algorithm. The simple algorithm has a broken node in it, and what happens when we execute it on the sort of each node has its own algorithm that they're executing, right, rather than the top down. the list eventually does get sorted, with the one broken thing just being out of place. But something crazy happens. Wait for it. This is going to blow all of your minds. This is a crazy thing that happens. If I was to graph, right, I was to put up a graph of how sorted the list was, right? It starts out pretty low on the sortedness scale because it's sort of randomly scattered. It's not sorted yet. That's not surprising to anybody. And that sortedness is increasing over time. But then something weird happens as we run into that one cell that just doesn't move, right? It's stuck. Sometimes we're swapping things over it that shouldn't get swapped over it because it's stuck. And what happens actually, the sortedness goes down for a period of time, and then the sortedness goes up to whatever the final level, the most sorted list can be. It's not perfectly sorted, right? Because we have this broken node in the wrong space. And let's just zoom in and think about what's happening when that sortedness goes down. So what's the job of the algorithm? The job of the algorithm is to sort the list, right? But what we're seeing is that the algorithm in executing it is doing something against sorting itself. So it's supposed to sort, and it does something that actually reduces sortedness. And what does that sound like? I'm listening to you. I heard all the audience members say this. That sounds like delayed gratification. The same kind of thing that happens when I decide not to eat that, extra piece of candy right now because I'm going to be happier later. I'm delaying gratification for my own good. And that's what this algorithm is doing. So we are observing in real time, this simple freaking algorithm is delaying gratification to get a better outcome in the long run. Are you as floored with how cool that is as I am?
Not even a little bit.
Let me say it again. Maybe I just didn't pit. No. Okay. Why not? Why not? Why are we not compelled?
Well, so to start with, it is not at all unusual in a normal sorting algorithm situation for there to be times when the sortedness of a thing gets worse before it gets better, right? So imagine the case where you got a line of a series of lines, right? And you're trying to sort from the lowest on your left to the highest on your right.
Okay.
Now imagine that the very leftmost element is number 2, is height 2. And the next one's height 3, and then 4, and then 5, and then 6, and so on and so forth, right? And then the next to last element is height 150. And then the very last element is height 1.
Okay.
That list is very sorted. All but one element are in the right order, right?
Yeah.
Then you do a bubble sort. And what a bubble sort's going to do is it's going to swap the very last 2 elements, right?
Yep.
So now you have n minus 2 elements that are all sorted correctly, and the last 2 are wrong, right? You do another pass through the bubble sort, and now the last 2 elements are correct. The third from the right element is wrong because it's the shortest number. And then all the ones from there all the way to the beginning are sorted correctly, right? So now you've got 2 that are correct, n minus 3 that are correct, and 1 that's wrong, right?
Yep.
So now things are worse, right? And so as that smallest element gets bubbled one run at a time, 1 to the right and 1 to the right and 1 to the right, the number of elements that are correctly in order will go down and down and down and down and down until finally we get to the very end, and then click, all of them are going to be sorted again correctly, or all they're going to be sorted correctly for the first time. Right. But that entire pass, every time, because of the pathological case of the way that got set up, which can happen randomly, although it's not very likely, every time that you pass through that algorithm once, then it's going to be sorted less, it's going to have less sortedness than it did the time before. Right.
Yeah. And the thing that this points to, my biggest issue with this one, right, is that the starting the thing that he smuggles in this argument. And again, to be clear, I've listened to him tell the story tons of times. I'm pitching it the way that he pitches it, perhaps even more charismatically. But that's just me. He says the thing that this algorithm is trying to do is to improve the sortedness, and what you're pointing out is nowhere do we give it a scoring function. Right? This is not a machine learning algorithm where we have some sort of scoring mechanism that says the thing you do is good when this goes up or bad when this goes down, and that's reacting to it. No, It's just executing a series of steps. And it's doing that exactly the way as indicated in all of these cases. And that's something that Mike would also say and says over and over again. There's no magic here. It's just doing the steps, etc. And so the fact that there are other like top level metrics that we could apply and look at and notice that they move differently is not surprising at all, and like totally unrelated. Maybe it's a little stronger than that, but more or less it's orthogonal to the algorithm as a whole, right? You might say that if what I want, right, is the boss might come in at any moment. I'm doing some work. I'm ordering this list right now, and I don't know when the boss is going to come in. And when they come in, they are just going to pay me based on how sorted the list is at that moment. What should I do? Then I might suggest a different algorithm, right? Especially if I'm in the case that you're talking about. I might be like, don't move anything. Because if I move something, then I'm going to decrease the algorithm, the list sortedness. I'm okay taking the paycheck right now when it's not perfectly sorted because it's close enough, right? There are all sorts of different ways we could apply, like practical considerations we could use to apply these algorithms. But in the case here, no dice.
And for the record, that's actually a situation we run into a lot. And you'll hear it talked about in an AI context. So there's this concept in AI called gradient descent, where basically what happens is as you're trying to find the fitness for a particular thing and you're trying to answer the right questions, you try to minimize a particular function. They call it a fitness function, but basically you're trying to get to the best value of this function to decide what the right answer is, right? And there's this problem in that case of what they call the local minima, where basically imagine a roller coaster, right? And imagine you're trying to find the lowest spot on the roller coaster. And imagine the roller coaster has two big humps on it, right? Well, you go up the first hump, you come down, you're now in between the humps. If you try to go one direction, you go back up the next hill. Well, that's not right because that's too high. So you try to go the other direction and you're trying to go back up the hill you just came down. Well, that's not right. That's too high. So you're stuck right there in between these two humps, even though that particular spot might be higher and probably is higher than the place that you started the roller coaster, right? But because you're trapped in this local minima and you're trying to do this algorithm where you're saying basically, well, if I go a certain direction in this, if I go a certain distance in this direction and it keeps going higher and higher, then I'm going the wrong direction, go the other way. Then you end up in this spot where you land in the wrong place because you never looked far enough out to see if there was a place below that. You're stuck in this local minima.
Yeah.
Right. And we run into that all kinds of fitness functions, and it happens in AI a lot. And you'll hear them in the gradient descent and then the local minima problem.
Yeah, very, very similar to like using Euler's method to find zeros of a function,
right?
Where you just take the linear slope of a function at any given point, and then you trace that back to the y-axis or to the x-axis, and then you see is that the zero, and you can keep tracing. And that's a really good way to find zeros in some cases, but it can totally screw you over in other cases when the function has weird shapes.
Right.
But yeah, same kind of idea is going on. All right. So you're not moved by delayed gratification.
Nope.
And we could also talk a little bit about, is this really what delayed gratification is? Like, how are we defining it in this abstract way? I'm going to set that to the side because I'm going to put my Mike Levin hat back on, and I am going to wow you with like delayed gratification. That's kind of cool, but that is not as cool as this next thing. This next thing is going to blow your mind. So here's what we did. Now, and you might be thinking, okay, great. We, instead of top down, we're doing this bottom up thing where we give each individual node its own rule, and we had them do bubble sort. But what if, instead of giving them all bubble sort, we give them different algorithms to follow? So node 1 might be a bubble sort, and node 2 might be an insertion sort or whatever, right? We can give them different commands and then execute it. And that's what they did. They did that, and the list still got sorted. Pretty cool. So this allows us to get, again, like different way. Even if they're trying to sort the list in different ways, they're able to work together. And we can maybe say some like cool metaphorical things about all of us people in the world have like different aims and different ways about going about life, but we're still able to like ruin the environment together. Like it's kind of neat how we're able to get there. But then the next move is that he observes another property about these nodes, which is let's measure over time how sorted the list is but let's also measure over time how close together the things are that are following different algorithms. And he comes up with a term for this. He says a given node's algorithm that's following is its algotype. So, for instance, if the number 2 was first on our list and it was doing the bubble sort algorithm, we would say the first node, the 2 node, has an algotype of bubble sort. And so what he does is he computes how close are the bubble sorts together and how close are the insertion sorts, et cetera, together. And he measures that over time.
What does together mean in this context?
It means, are they, I believe it's, if a given node is bubble sort, how likely is it that its neighbor is also bubble sort?
Okay.
Bunch of ways that we could measure this sort of thing, but we're looking for clusters of things that have the same algorithm. And the starting assortment of clustering is nil, right? They're randomly assigned the algorithms. And the end assignment is also randomly assigned what the algorithms are, because, you know, the sortedness of the list is independent of the algorithms that are going on. But what they find is over time, as the list becomes more sorted, right? In the middle there somewhere, actually the things that have the same algorithms are more clustered together. So the clustering of algotypes goes up, and then it goes back down to pure randomness at the end. And this is amazing, because what this shows us is that in the algorithms that I gave them, I didn't tell them anything, right? I didn't say, bubble sort ones, try and hang out with your bubble sort friends or anything like that. It's totally agnostic about the algorithm types of the other nodes. Mm-hmm. And yet, as we observe this list over time, we see that they are clustering together, which tells us that the computer is doing something we didn't tell it to do. It is expressing, in a way, we can see that it desires to cluster together algorithms that are similar to one another. And so what we're observing here is that computers have, not maybe desires in the same way that I really desire a piece of cake right now, but they have desires and preferences for certain states and are doing things above and beyond what they're asked to by their algorithms. And this is evidence of some sort of proto-mind that's going on in the machine. And I can tell from your face that you're sold on this one. And you,
yeah. Okay. So remember back at the beginning when I was talking about how, in order to do science, you have to create a hypothesis about what you think is going to happen, and then you have to run the experiment, and then you have to decide whether your hypothesis is correct based on what you observe in the experiment. And that by running an experiment and then cherry picking the result of the experiment to go, oh, look at this cool thing that I found, that you're not really doing science, you're just p-hacking, or you're just, deciding after the fact what the right answer was.
Are you saying you were foreshadowing at the start that you already knew what was going to be wrong here?
I actually was not expecting it to come up at this particular part of the conversation, but yes, there's a lot of, not just kind of anthropomorphizing the desires of the thing, which is a problem that we always have when we're talking about especially AI. But there's a lot of after the fact, saying, oh, look, I discovered this new property of a thing. And so my guess is that I could spend some time constructing individual algotypes that would have the property that they would not cluster. Right? That, I could create algotypes in such a way that, not that don't intentionally try not to cluster, right? But that have a property of, because it's looking for, the element that's 7 away from it or something like that, right? That don't end up landing next to each other because that's just not the way that algorithm happens to land. And my guess is that this idea of them clustering together is largely a function of the particular way that they were. It's a particular element of a particular algorithm, but it's not a desire of the whole system. It's not a particular desire of the of a particular algotype. It's that this particular algotype happens to have an algorithm that happens to cause things to cluster under certain circumstances, and maybe even under other circumstances. The way that I particularly picked the pathological version of the bubble sort, where the very, very last element should have been the very, very first element, I probably could pick a particular starting situation which they wouldn't cluster at all.
Right.
And the other thing is that, I mean, again, in this paper, they don't give code. They give some examples of like, okay, here's what we say the graph is. They don't give really good examples of exactly what happened. And there are some things that they say that they assert to be true that like there's no evidence for, and given the explanation that they've given, don't seem to be possible to me at all. And so there's a lot of elements of this, or a lot of claims in these papers that just like, I don't, so for example, if you take an element and you don't let it swap, right? So this element's always going to stay in the same place. All a bubble sort can do is swap with its nearest neighbor.
Right.
And so if its nearest neighbor can't swap, right, there's no way for the list to get sorted across that neighbor, because
So just partition it.
It basically just breaks the list in half, or in thirds or in quarters, depending on how many elements there are that don't move, right? But there's nothing in the paper that talks about that. When it gets to the point where it's talking about, the list got sorted anyway, well, now he's jumping to insertion sort, but he's still talking about how resilient, quote unquote, the bubble sort algorithm that they used, the individualized version of the bubble sort algorithm, how it was more robust or, resilient to these frozen elements than the larger element, the larger algorithm, the 6-line version. But given the explanation that he's got, I don't see how the bubble sort, the individualized version of a bubble sort, moves at all. On either side of that element, I don't see how it would get sorted. It would with an element in the middle that can't move, and you're only allowed to move one element one way or the other. What you're going to end up with is, two lists that are independently correctly sorted that are separated by an element in the middle that doesn't move, which is not at all what the way I would describe as being resilient to an element that doesn't move at all. So
either we've got a dilemma, right, where either it's not sorted in the way that he's saying by the end, or the algorithm or like the way that they're executing it that allows it to be more robust to that frozen unit is not described. But that just tells us that the algorithm, the code, whatever that's being used here is more sophisticated or handles more cases than the original stuff. And that itself means that they're taking too much about the resiliency of this approach.
Or they're doing the thing that the AI people love to do, which is basically using a word that's ill-defined in a way that they're not specifying, where it can mean more than one thing. They're not going into detail about exactly what robust means, or exactly what artificial intelligence means, or exactly what an individualized bubble sort means, or an agentic bubble sort means in this particular context, and then making assertions about it, causing the reader to draw conclusions that may or may not be at all valid, because the amount of detail that you'd have to have in order to understand exactly what the assertion is just not present.
Yeah. Okay. There are two reactions that I had to this that I wanna throw out for you. One is a hypothesis, and another is a proposed experiment. I want to get your sense of how these would respond to Mike's view. So the hypothesis was, the first time I read this, I thought, okay, the reason that clustering is probably happening is that bubble sort or insertion sort, or like these different sort algorithms, some of them are probably just a little faster than the others, or maybe like faster for the extremes. And so as those elements race to where they're going more quickly than the other ones, the things that are kind of left behind are more likely the slow algorithms, and so they're more clustered together. Does that seem plausible to you?
Yeah, absolutely. So if you think of, so this is kind of a weird idea, but think of of a sorting algorithm or an algotype of having a speed or a velocity, right? So the idea being that if you've got a bubble sort, each step, each element can move exactly one space, one direction or the other, right? Because all it ever does is swap.
Right.
So it can move one space to the left, and its neighbor to the left will move back to its right. Or it can move one step to its right, and its neighbor can move one step to its neighbor's left, right? It can move exactly one space per step. That's it, right?
Good. Yeah.
Then you take something like an insertion sort or something where basically you you look and you find the element that's the smallest element in the whole thing, right? Pick it up and put it in the space where it's supposed to go.
That has high velocity. That's a teleportation velocity.
Exactly.
Yeah.
Right. And so it turns out that the things where you're just picking up the longest element and sticking it on the right, and you're picking up the lowest element and you're sticking it on the left, right? Those things are going to jump way the heck away from the things that can only move a little bit at a time. Right. And especially when you're in the case of you're intentionally trying to say, okay, I'm going to start sorting from this end, or I'm going to start sorting from that end, and I'm doing a sort where I'm grabbing an element and throwing it all the way over to one side or the other, right? It's very much the case that, the elements that can only move a little bit at a time are going to stay more or less close to where they started. And the elements that are all the way on the right are going to get really close to each other, because basically this element is like, oh, okay, I'm the longest one. I'm an insertion sort. I'm going to pick myself up and I'm going to throw myself down at the end. Oh, look, I'm also an insertion sort. I'm going to pick myself up and throw myself next to the one that's on the end. Well, of course, those are going to be close to each other.
Yeah.
Right.
Good. And this, it all has the vibe to me of, we can take any story we want that has some order to it. We can throw some extra metadata on it and then observe some new order about those things. Like, picture, watching a sheepdog herd some sheep into a pen, right? And we could watch it happen and we could look for patterns. Great. And there might be some meaningful patterns. We're like, oh, notice the slowest ones are usually on the right or whatever. And maybe that's useful. Cool. And then we could take those same exact sheep, right? We could run the same video back and we could color each one of those sheep, some blue and some red. And then we could observe what happens. And it might turn out that there were some weird, quote unquote, emergent properties about the red ones clustering or whatever. But we could add that after the fact and find all kinds of crazy correlations or pretend like they were telling us some sort of story.
Yeah.
This, I think, has the same kind of vibe that you're saying. This is the p-hacking element of what's going on. We can apply infinitely many metrics on top of this sorting algorithm and then look for changes in those and look for correlations. But to pretend like something else causal is going on there becomes implausible to impossible with the level of speculation that's going on here and sort of the ad hoc reasoning.
Yeah.
Here's the other.
And if you wanted to take this and do actual science with it, right? What you would do is you would do this experiment, right? You would say, okay, so I'm seeing this clustering behavior. I'm going to come up with a hypothesis as to why this clustering behavior is happening. And then I'm going to create a new experiment that then will either prove or disprove or provide evidence for or against the hypothesis that I have that says that the reason this clustering is happening is because this algotype wants it to happen. Right. And then you do the second experiment and you see whether or not that hypothesis is borne out by this new experiment that you've created that's specifically designed to decide whether or not algotypes want to or have a desire to be clustered together or not. Right. And one of the things that you would do in that kind of case is you would say, okay, let me try to come up with some counterexamples. Let me try to come up with some alternate kinds of algotypes that might not want to cluster with each other. Let me run that kind of experiment and see if they still try to cluster together or that kind of thing, right? But that's not what happens, right? He's not taking this observation and saying, okay, now that I've observed this thing, let me create a hypothesis based on that observation, and let me run experiments to decide whether that hypothesis are true or not. He's just saying, oh, I made this observation. Observation is consistent with this hypothesis that I didn't create this experiment in order to verify. And so therefore, I'm going to assert that this hypothesis looks to be true when that's not an experiment, when the experiment that I'm running was not designed to prove or disprove the hypothesis that I'm currently asserting is being borne out by this experiment.
The other thing I want to throw at you, my hypothesis. So here's the experiment I would like to run, and I haven't done it yet, so I'll just use it as a thought experiment, but I think it'll be pretty effective. So let's take some list of numbers, whatever list he ran, and do the same thing that he did, and we'll observe the clustering. The clustering happens. Let's just take for granted that did. I don't think he's lying about his data in this case. Now, let me take note cards, like physical note cards, and I'm going to write the numbers and the algotype on those note cards, and I'm going to lay them out on a table in exactly the order they had listed initially happened. And then I am physically, with my hands, going to execute the algorithms as it was described, right? So I'm going to, all right, card A, you're doing insertion sort, you're jumping over to here, etc. And we can take snapshots of that after each step. And what's going to happen, and I think Mike would even agree that this is going to happen because he says there's no magic here. They're just doing the same, like the algorithms are being followed in order, right? If you look at those note cards over time, they are going to observe the exact same sort of clustering over time as that list of note cards gets sorted, right? And now Mike is in a bind because either he has to argue that, yes, the computers are expressing their desire to have clustered nodes, but then he also has to think that my note cards on my table have a desire to be clustered in the middle of this process in the same sort of way, right? Like the thing that he's got, I think if he actually tries to attribute the mental contents to the computer, he's not going to get there. The mental contents have to be attached to the algorithm assortment, which is bizarre and useless at best.
So you're creating the Chinese room version of the sorting experiment, right? Where,
yeah.
You know, I'll stick something below about the Chinese room. I've got a really good explainer video from the BBC on it, but you want to give us a 5-second kind of...
And I feel like we should do a full version of this at some point. But essentially...
we should definitely do a whole episode on the Chinese room. It's very interesting.
Lock a guy in a room. He doesn't speak any Chinese, doesn't know Chinese at all. There's a bunch of books on the wall, a bunch of instruction manuals. Someone slides a piece of paper under the door. It's got some symbols on it. He looks at those symbols. He goes to the books on the wall, finds those symbols, and they have when you see these symbols, give these other symbols out. So he writes the symbols he's supposed to write to go out, and he shoves them out the room. Turns out later, for someone who speaks Chinese, it looks like they're having a conversation. They say, "Hello, how are you?" And they slide it under the door. And in Chinese, he sends out symbols that say, "I'm doing quite fine. It's a lovely day," or whatever, right? So he engages in a process with the books on the wall and himself in the room that he is sending out symbols that look as if it's having a conversation. And then there are questions about it like, does the guy understand Chinese? And most people say, nah, the guy doesn't understand Chinese. And there are questions like, well, does the room and the guy composite understand Chinese? Do the books understand? So it's meant to evoke our sense of what constitutes understanding and sort of mastery of a language. And then there's an obvious analog to computers here as just sort of symbol manipulators and matchers. We don't, if you don't think the Chinese room understands and the guy doesn't understand, then you also think that the computer machine doesn't understand either. It's just doing the same process of input-output matching. Yeah.
The alternate explanation is that basically you become the substrate. Congratulations. Right?
Oh, I suppose, you could say that, is that I have a desire for them to be clustered that is realized through this process or something. Yeah. For the record, I don't desire for any sort of algotype clustering. But maybe I'm just blind to my own preferences here. Yeah. I don't have access to that.
Again, this is the Chinese room experiment, right? And so all of the different various ways that the people that believe that the computer actually does have some understanding and that basically the act of coming up with good responses to a thing indicates that there must be some understanding happening somewhere, have all kinds of gyrations that they have to go through in order to try to figure out how this Chinese experiment, this Chinese room experiment would work. Some of them basically just asserting that there is no Chinese room version that's if you actually tried to do that experiment, it wouldn't be possible. And so without some kind of understanding. And so, the whole thought experiment is invalid. There are lots of different, like I said, we should have a whole episode on it specifically, but that's effectively what you're doing, right? Is you're coming up with, you're intentionally inserting yourself in the spot where the understanding or the intention would be, and asserting that you, being in that spot, do not have the understanding or the intention that is presupposed by this argument, and so obviously that means the argument must be invalid.
We're going. It's the substrate independence piece,
Right.
That we say, okay, look, this algorithm can be carried out by a number of different mechanisms. And so if we want to say that the algorithm's execution in a given case and some, correlations within it reveal preferences of the system or of the machine, then I think he's going to be forced to say that any other system that executes that algorithm would also have to. But the push here that you're saying is, I say, clearly these other things don't have that desire or feature. And so, reductio against his view that the computer itself has desires for clustering. Okay, excellent. There's one last piece here that he goes back to that I want to mention, which is if we see this like emerging desire that shows up in the clustering, right?
Mm-hmm.
But it goes away by the end of the experiment because now it's fully sorted, and so that correlation is gone. His thought was we can reveal this preference more clearly. We can sort of take some pressure off of the system to allow it to keep expressing its desire by having repeated digits. So if I have 5 5s, or 3 2s in my list of numbers, and those 2s all have different algorithms, then those 2s could be sorted any way I like in the final sortedness of the list, right? So if I have a set of numbers 1 2 2 3 4, it could be 1 2 2 or 1 2 2 with the 2s reversed. It doesn't matter in the sorting algorithm.
Mm-hmm.
And so having repeated digits allows him to say those 2s, if they had different algorithms, could have had the algotypes be in either order.
Okay.
And so he makes the list have repeated digits that have different and similar algotypes, so we can see if the clustering persists at the final stage. And that's also what he saw, is that the within the repeated digits, things that were of the same algorithm sort, algotype, were often clustered together still. I can't tell if your confused face is because I didn't describe that well enough.
No,
why he would think that.
I understand what you're saying. I'm trying to decide what the value of that is. I mean, so like I said, it makes perfect sense to me that algotypes that have a higher velocity, right? Things that can jump the entire length of the array in one step, are going to be closer together in their final place than algotypes that can only move one step at a time. Right. And so I can certainly imagine a case where it's really just a function of the velocity, right? I mean, what you're going to end up with if you've got a bunch of 2s is basically, you're going to have the things with higher velocity, I would think, on the edges of the block of 2s, because they jumped from way away.
Yeah.
Right. And then the things that moved very slowly are going to end up being more or less in the middle of the 2s, because other things are going to jump kind of close to each other, right? Because presumably, it actually isn't defined, but basically, so if you're a 2 and the 2s, if you're element 85, right, and you're a 2, and the 2,
I've been told that I'm at least an 8, but sorry, yeah, go ahead.
And the 2s are currently in between elements, 6 and 13, right? The question is, do you jump from element 85 to 14? Or do you jump from element 85 to element 5? Do you jump to the beginning of the 2s, or do you jump to the end of the 2s? That's not specified in the case of duplicates. Right. So you'd have to decide in that case which one you would want the algorithm to go to, or just have it, picked somehow. But my guess is that the ones that are coming from a long way away that are making some decision about where in the group of twos they're going to land are going to, the ones that are, like, so for example, say there's an algotype that's I'm going to jump to where the twos are and I'm going to jump to the rightmost element of where the twos could be. And then you have another algotype that's like, I'm going to jump to where the twos are, but I'm going to jump to the leftmost element of where of the group of twos. Well, the ones that go to the leftmost element of the group of twos are going to be on the left, presumably. And the ones that their algotype is to jump to the rightmost element of where the twos are largely going to be clustered on the right. That's not a function of, a desire to do that. That's a function of basically how you picked which element they're going to insert themselves into.
Right. And I think if you have bubble sort there too, right? Like you'd actually have the insertion sort left and insertion sort right would end up on the left and right side of the middle, because then the bubble sort guys will all arrive later and sort of sandwich them in from the side.
Yeah, and the bubble sort guys, and the bubble sort guys, if they end up in the middle of the twos, aren't going to move. Because a bubble sort guy, if it looks on the left and there's a two, and it looks on the right and there's a two, it's like, cool, I'm sorted correctly. I'm not going to care about anything else because I can only see one element on either side of me. Yeah. So they're just going to sit there.
Yeah. Good. Okay. So this has been sort of unpacking, and this is the core argument that he makes. Now he makes this with some other examples and things in other places, but this is the one that he always comes back to, this bubble sorting algorithm thing, because he thinks it's very powerful, or at least this is what he claims. Mm-hmm. Also, I mean, when I'm looking through his other data, I think it's I don't know whether I say it's the strongest case, but it's certainly the one that he says the most about, or he thinks is the pithiest, or that he has the most published on. And so he's just going to bring it up a ton.
And he keeps going back to at least in what I saw, he keeps going back to the idea that this is just 6 lines of code over and over and over again. It's like, okay, this happened, but it's just 6 lines of code. And he gets more and more convoluted versions of this. Right. And then still jumps back to, this is coming out of 6 lines of code. It's like, it's not coming out of 6 lines of code.
Maybe it's a really long line. Like it's just six lines, but the 6th line is just, you couldn't fit it in a tweet. Okay. So then I want to sort of summarize from his perspective what he takes the main takeaways this to be. And I think we've responded to a lot of these. Some of our responses here can be quick. And the first thing I want to do is just read from some personal correspondence I had with him, what he takes to be the summary, so I'm like extra clear that I'm being charitable to him. I don't know if you want to read this or you want me to read this.
I can read it.
All right. Go.
Quote, bubble sort was invented in 1956, and a generation of CS students have studied it. Everyone thinks it's well understood, deterministic, transparent, and simple. In 2025, we found new properties in it that are not at all apparent from the algorithm itself. Specifically, not simply side effects like complexity, unpredictability, etc., but properties recognizable to behavioral scientists. Therefore, even some simple familiar systems can harbor unexpected and previously undiscovered proto-cognitive competencies. We found them precisely because we were willing to examine them from a different perspective, because we didn't assume the algorithm tells the whole story. Unquote.
Okay, so that's Mike's take on this stuff. We have a simple thing that we thought was well understood. We looked at it from a different level of selection, right? This is the sort of supervenience kind of picture. We saw stuff that other people had just missed, namely that there's behaviors that any good behaviorist would look at this and say, we see avoidance behavior, we see delayed gratification, we see desires expressed for clustering. And this tells us that they have minds or something like minds, like proto-cognitive capacities. That's what's going on. That's what Mike takes us to be. And I don't know if you have any specific response. I feel like in general, we've rejected all of that pretty soundly so far.
Yeah, I mean, I would say if you want to assert that these are emergent properties that are indicative of behavioral science, that it is incumbent upon you to take that hypothesis and attempt to construct experiments that could disprove that hypothesis, and then do those experiments, and then publish and explain why this experiment could have disproved this hypothesis, and why it didn't disprove it, and why it in fact provided support for it. And I have seen no evidence that that has happened. What I have seen is he did an experiment, if you can call it that. He saw stuff and said, that looks like thing X. Therefore, underlying mechanism exhibits the property of thing X. Without saying, if it were true that underlying mechanism actually exhibited the property of thing X, then these experiments would reinforce that, and these experiments would falsify that. And so let me run those experiments and see if I can support or refute my hypothesis. And I have seen no evidence that that's actually happened.
Yeah, the way you put it there, I think captures something that has had me feel really conflicted about this. Because I've gone back and forth from saying like, oh, this is frustratingly bad, to like, there's something really cool about this. And I think the thing that's really cool is, yeah, look, you put an extra metric on top of this, you looked at it, you noticed a correlation, you were curious about it. You're like, I wonder if something's going on here with how these things are clustering. And I want to encourage that kind of thinking. I think that's good, right? Like, play around with something that seems simple and enrich it a little bit, see some behaviors you didn't see coming and be like, whoa, what's going on there? But it feels like that's where we're at in the experiment, right? Is our curiosity has been piqued by poking around at a thing, and we haven't done we're to the hypothesis stage, but we haven't gone beyond the hypothesis stage. And the thing that's so frustrating to me is the depiction of it and the publications of it and the going on podcasts and shows to talk about it is pretending like the science has been done and there's more exploration to do, but we've run the experiments and we found the thing. It's like, no, you've gotten almost to a hypothesis. Like, you're just starting it and you're pretending like the job is finished, right?
Right. And in that process, you are making assertions about what you discovered without presenting enough underlying detail for people to follow along with your work and decided whether or not they agree that what you actually discovered was actually present, because you're glossing over a bunch of the details that would be required in order to find out whether or not your presumption is actually true. What would be really interesting, which, assuming Mike is actually watching this, which I doubt, but we're assuming that were to happen. Hi, Mike. What would be really, really interesting, right, is if you were to take an algorithm that already had a bunch of individualized decision points, right? So instead of taking a really simple algorithm like a bubble sort, and then carving it up into a whole bunch of different agentic kinds of bubble sorts and then trying to do something with it, right? And then assuming that or presupposing that this new agentic version of the bubble sort is something that came out of the original bubble sort, right? If you were to take an algorithm that already was divided up into a bunch of little chunks and then look in it for kinds of emergent properties, and then find hypotheses about that, and then try to support or refute those, that would be far more interesting than keep going back to, it's only 6 lines of code, because that's garbage, right? Yeah. What would be really interesting, the reason I say this is because we have a lot of really important algorithms that take a problem and divide it up into a bunch of tiny little pieces and to run on graphics cards or on, AI processors, namely all of the matrix multiplication and those kinds of things that happen in a large language model kind of context and in a transformer context, right? And if you were to take those kinds of algorithms, right, and you would observe useful kinds of behaviors as a behaviorist or a behavioral psychologist, behavioral scientist, if you were to find things that a behavioral scientist would see out of this kind of a mechanism, right, that might be really interesting. We would find out some interesting things about the way that these algorithms that get divided up into tiny chunks and run on graphics processors would behave in ways that nobody's really looked at before. And I think that would be much more valuable and potentially give us some insight into how we might optimize those algorithms or how things might be interesting about them, in a way that trying to deal with this juxtaposition between it's only 6 lines of code and, oh yeah, we completely rewrote the entire thing so that everything's agentic, but we're still going to go back to believing that it's a really simple algorithm that's only 6 lines of code. That's, there's a lot of stuff there that lends itself to lots of kinds of errors of type and errors of assumption, that would not be the case if you actually started with an algorithm that already is in a way agentic, or at least divided up into a lot of little independent pieces and then put back together.
Okay. There's one type of argument that he makes a lot that we haven't touched on at all here yet. And that is, other than in the preliminaries, and that's talking about the Platonic space. And so what he claims is that if what we see going on here is not explained by the algorithm, because the algorithm makes no reference to algotypes, for instance, and yet they're still clustering by algotype. So if we're going to buy in that there's something going on above and beyond the algorithm, where is that happening? And he says that's in the Platonic space, right? The mind or proto-cognitive capacity, right, faculties of this machine that's executing the algorithm that has a desire to cluster, or that has a desire to do whatever desires these computers have. We can make a use of that Platonic space for quote unquote free compute, right? And so, I mean, the thing that threw me out, like when I first listened to this, I was like, we're making a computer perpetual motion machine here, right? That's kind of what's going on. But if there are tendencies that show up in these algorithms because of the way computers want to do things, then we can write code more efficiently, because we don't need to tell it to cluster stuff. It's just, it wants to do that anyway. In the same sort of way that, like, oh, I don't have to tell my kid to eat the carrots. I can just put the ranch dressing on her plate, and she will use the carrots as a spoon to eat as much ranch dressing as she wants, or whatever. Like, it's a parenting hack. Like, he thinks we have this for our code writing, or something like that. So I don't know that I have anything else to say about that other than the potential of a perpetual motion machine in this context is enough for me to say you have to know your view is crazy if it would have that sort of implication. But I think we've already thoroughly rejected all of the bases for thinking that there's something above and beyond going here.
Yeah, I mean, so one of the things that happens in, and I kind of alluded to this earlier, one of the things that happens in algorithms is there are a lot of different algorithms that have particular pathological cases, right? So, like, there are times that, if you want to use a particular sort, and it turns out that the original distribution of the things that you're trying to sort happens to meet this particular set of criteria, right? Then the particular algorithm that you chose might be way faster or way slower than it would be on an actual random set, right? So, for example, when I said that the pathological case for the bubble sort is it's all sorted except for the one element that's in exactly the wrong place, and it'll only move one spot per step, right? If you have something that's, all but one of them are correctly sorted and the other one's in the worst possible place, the bubble sort's the worst possible algorithm to pick for that, right?
Yep.
It's possible that what he's kind of that what the result of such a free compute would be is less along the lines of a perpetual motion machine and more along the lines of, okay, in this particular kind of case, right, it turns out that this particular sorting algorithm does a much better job or a much worse job for this set of initial conditions than it would have for, an arbitrary set of initial conditions, right? And so there are times when you choose what algorithm, and this isn't necessarily true for just sorting, but there are times when you happen to know that the data that you're dealing with happens to be in a particular form. And so you want to pick a particular kind of algorithm because you know that for that particular form of the way that the data happens to already be arranged, the algorithm that you're going to use, even though in any arbitrary case might not be the best algorithm, it's going to be the best algorithm for the one that you're currently, the data, the kind that's structured the way it's currently structured.
Right. But that's not, that is important table stakes for being a good computer engineer, right? Is like to know what types of algorithms or what types of programs are better or worse in certain circumstances. You don't think of it as leveraging the mental contents of your computer. You think of it as picking the right tool for the job.
Right. I'm just saying when he's talking about free compute, that doesn't necessarily mean, something as inane as a perpetual motion machine. It's conceivable that his idea of free compute actually maps to some idea about how there are certain algorithms that are coincidentally happen to perform particularly well for a given structure of data that they're operating on.
That's fair.
That you didn't intend for that to happen, right? But or particularly badly, right? But if you happen to have an algorithm that works particularly well with a particular set of data, that idea of, this algorithm normally would complete in order n squared, but in this particular case, because of the way that the data happened to start out, it happened in, order of log n or even order constant. Right. That feels like free compute when it happens in the wild. And then you go and dig in and go, okay, why is this happening so much faster than I expected it to? And you go, oh, okay, it's because it just so happens that the way that, for example, the way that this data was coming back from disk, because of the way that the different kinds of, because all the A's ended up on this disk, and because all of the B's were written to that disk and all the C's were written to that disk, when I pulled them all back, it turned out that all the A's happened to be over here mostly, and all the B's happened to be over here, this source mostly. And so the sort that I expected to not be all that efficient turned out to be really, really efficient because everything started out a lot more ordered than it would be if they came in random.
Yeah, nice. So I like that, and I think that is like a useful takeaway, and also probably more charitable to Mike. Having watched and read a lot of his stuff, I really get the sense that he's got the more magical thing in mind. But I'll get back to that in just a second when we talk about like some big picture takeaways here. The other thing, just once we have this Platonic space, this room, this type of argument, I think it's worth saying one implication that Levin thinks is happening here is what we see is that we ask the computer to do something. It does that thing exactly as we asked. But we see these variations, and in that space, that's where we see the mind or the semi-cognitive things. He thinks that might well be true. Now let's be good scientific method hypothesis people and say that could be true about everything, right? Like this coffee mug, this little cute little cat toy that I have on my desk. All of these things, right? They're obeying the laws of physics. They're obeying the various commands that they have to. But in that liminal space, in that Platonic realm between what they have to do by following the laws of physics and other things, that's where we'll see their proto-cognitive capacity. And this is where his panpsychism comes in, right? Where panpsychism is just like everything's got a mind. And, it's already been a super long podcast. So I don't want to go too far into that sort of thing. But that's the picture that he's ultimately advancing, that's sort of driven off of these kinds of examples. And then it's almost trivial if you're taking that case to think that LLMs have minds, and a bunch of these systems are certainly more complicated.
Sure. But I mean, if my coffee cup has a mind, right, then the property of having a mind transmits no benefit. right?
Yes.
Right. Because, everyone will agree that, I don't need to be particularly nice to my coffee cup. Right. And if I decide that I get a better coffee cup, that I should not feel guilty at all about getting rid of the coffee cup that I already have, aside from the whole, adding things to the landfill kind of thing. But that's not a function of the coffee cup. That's a,
Your coffee mug is so hurt right now. It's
yeah,
listening to you
right.
say this. It's just
But
devastated.
but that again, my coffee cups are stainless steel, and stainless steel recycles really well, so I don't have any guilt in getting rid of one coffee cup and getting a different one. So
If everybody's special, nobody is, right?
right,
If everything's got a mind, then what work is that doing for us
yeah,
anymore? It's nothing.
yeah, and if everybody's special, then special loses its meaning, right? And so the idea of of AGI, right? I mean, if having a mind means something's closer to AGI, and the property of having a mind is something that is attached to my coffee cup, then the fact that it has a mind under this definition of mind means that a large language model is no closer to AGI than it was, because my coffee cup is no closer to AGI than any other block of stainless steel.
Yeah, yeah. And we're going to invent some new term that says, okay, yeah, like, look, your mug's got a mind. So does my cat toy. So does the painting on the wall. But there's this other thing. It's a schmind, and this is the kind of thing that you and I have that those things don't have. And what if we made computers that had schminds, and we have a schmind I, and like now we've just like pushed everything over one level, right? Which is not to say that like there's a possible world, and you could try and make the case that this is such a possible world where rocks are sentient, where microphone stands are sentient. We haven't seen any evidence for that yet. And it can't just be that there are physical affordances, and of course they follow all of those, but in that liminal space, there's a mind. We just haven't observed it yet. Because if you're doing that, now you're just, you're doing all sorts of bad scientific practice when we get there.
Well, I mean, I have seen some people asserting that, to some extent, plants have minds,
mm-hmm.
right? And that if you speed up, the growth of a plant, it looks like it's got agency, and it looks like it wants to, grow toward the sunlight or that kind of thing, which is great. But, that doesn't mean that it's worth me starving to death because I refuse to eat plants, right?
Sure. And it begs for some, there could be some experiments we could run, right? Where like when we're able to actually now communicate with plants, and they explain that they have, real pain, and so like maybe we get there, right? But there's a lot more work to be done,
Yes.
as well as say on that front. So here's my overall stance on the Mike Levin stuff, and I've been super appreciative and have been waiting for a long time to have this conversation. So thank you, Carl. But where I think I end up on it is that there are two readings of Mike's view. On the one reading, he's talking about everything having minds and these algorithms and computers having desires in the real, like, deep substantive sense that I think of myself having those things. In which case, Mike's project is really, really interesting. Like, he's making bold, fascinating claims, and he gives us literally no reason to believe them, right? Like, the evidence is just vanishingly small. Like, I want it because that's crazy interesting if it were true, but like, you don't give me anything to sink my teeth into. Alternatively, he could mean that they have minds in the sense that, in the very loose sense, where there are some cases where the tool's better than other cases, or where we can redescribe the word mind in a very generic sense that includes all things, or we can redescribe avoiding or delayed gratification in a way that includes what's going on with the computer. And if that's true, I think he's right that computers have minds in that incredibly thin sense, and I don't care at all.
Right.
That's where I'm at.
In which case the idea of mind in that thin sense transmits no information,
Right.
and conveys no value. And so, sure, say whatever you want has a mind in that kind of sense, but that's not going to have any effect on anything.
And and so if I want to take the lens back a little bit here, because I think this is going to be a repeated message on this podcast and in conversations that we have. And I want to be clear, I like Mike. Like, I like his work. I feel like he's authentic and doing stuff that he thinks is correct. Like, I don't think he's a grifter. And there are other people that we're going to talk about that I think are like dishonest or grifters, right? I don't want to attribute that here or be mistaken for thinking it. But I think we can get some ideas for good ways to identify these sort of thin kind of claims that they're either thin claims or they're substantial claims without the substance behind them, right? Without the evidence. And that's when there's a redefinition of terms, like really frequently, in a way that seems like really deep and philosophical, but it just makes you feel a little bit off. When he starts talking about, isn't this just delayed gratification another way? Like, or what is a mind but a way to include an intentional directedness at the world? Like these kinds of vague redefinitions that allow to put more things under that heading. That feels very much to me the way you've talked about a number of times on your other videos, where we can just use AI to mean any of 75 different things. And it allows us to make the bold claims be substantial and also retreat to the easy to prove, conservative way of defining the thing. And so we can have our cake and eat it too, sort of play the shell game. The other thing that shows up here a lot is someone who has a profound conclusion for a field that's not their field, and they don't immediately bring in experts from the field. Like, I think it's telling. Mike Levin would not say he's a computer scientist. That's not his thing. And he brings that up several times over the course of things. In some ways, he thinks that's cool because he's like, this is why people have missed it, because they were looking at the wrong level of selection. But once you find that, you should be pulling in someone from that and be like, look what you guys may have missed. What do you think about this? Am I missing something? And like, that's just what I see in our conversation where I'm like, are you surprised by this, or would this be a plausible explanation? And like, yeah, it would. I'm not like moved by the Mike stuff. Like, you've got to bring people in who are experts at some point if you think you're able to, turn over something crazy in their field.
Yeah. There have been a lot of things in science where discoveries have been made. If you read Thomas Kuhn, The History of Science, it's a bunch of fascinating stuff, where basically someone who's an expert in one particular field has dropped into another field, right? And taken what they've learned from their past work and applied that to new fields. But it's very important that that's done in conjunction with local experts, right? That having a new perspective on an existing problem is very valuable to the people that are working on that problem, right? And you can create very interesting synergies there. But when you're standing outside of that field and you're lobbing assertions into that field in a way that doesn't make any impact on that field, and that the people in that field are not aware of, and you're not trying to collaborate with them, and then you're turning to one side and saying, hey, to the media and the press and your, podcast listeners, and saying, hey, look at all of these brilliant insights that I have into this thing that I have no experience in, and that I'm not engaging with any of the people that actually have any expertise in that area. That's not a recipe for, actual discovery. That's just playing semantics, I think.
Well, I don't like someone to say playing semantics as if that's a mere and small thing, as like someone who works in the semantic web. Like, semantics are awesome. Let's not downplay those.
Well, so yes, but a lot of times, so I guess when I say playing semantics, what I mean is, that's just doing what we were talking about earlier and taking a word that's ill-defined or has one definition, right? And then, pretending it has a different definition, or pretending it has several different definitions at the same time and bouncing back and forth between them. That's what I meant by playing semantics. I meant you're
right. And like, that's where you end up with people who are equivocating or just leading to a bunch of merely verbal disputes where talking past each other.
So as someone who studies semantics, what would be the correct way of saying someone who's intentionally relying on a poor definition or on multiple definitions of a word and not specifying which one they want, that if it's not playing semantics? Because that's always what I've, you know what I mean? That's the phrase I've always grabbed for something like that. What would be the correct phrase for that?
To be clear, I'm not super offended. I don't think that's totally wrong.
I understand, but
it's equivocation is what
equivocation.
I would say.
Okay.
Yeah. So to equivocate is to use the same term or word in different senses across the argument. And I think that's what's going on in a lot of these cases is, this has a mind, this has a mind, I have a mind. But when I talk about my having a mind, I mean it in a more robust or different sense than when I talk about, my computer having a mind or something else. And that change in meaning is giving us a lot of leverage.
I really appreciate that. I know that so those of us that are not in the philosophy field, right, have this tendency to refer to semantics or philosophy or those kinds of things kind of as if they're not important. I remember you did a video talking about the video that Hank Green did with one of the authors of If Anyone Builds It, Everyone Dies. In which they would get to a certain point in the conversation and say, well, but philosophers would worry about that. And you were like, but no, I'm a philosopher. You really ought to worry about that, right? And so one of the things that I like from our conversations is I get an opportunity to, occasionally I will say things as someone who's not in the philosophy field, and I'll use words, that I will use words the way that I would normally use them, or that people that are educated in what that word really means concretely would use it. And it's a good opportunity for me to say, okay, cool. What should I have said so that I don't keep poking the philosophers by using, because it drives me crazy when people use words that are important to my profession in a way that isn't valid the way that we use them. Right. So when I am using a word incorrectly, at least according to the people for whom that word is very important, it's very valuable to me to find out what the right way of saying that would be.
Yeah, I would say equivocation, or like you could also say that they're just playing semantic games or something like that, which is like using semantics, but like using it in a cheap and trivial way rather than in like the more grounded and robust ways. There's also a little bit of an irony in that, like, you use the word valid in that last description. And like, as a philosopher or logician, valid is when you talk about validity in an argument, that is always the term that mess people up the most because there's so many different senses of the word valid. But that's a different conversation. But so now we've learned Mike Levin's views. We've learned some signposts for avoiding getting sucked into that with some redefinitions, and also don't listen to people who are just like, hey, don't listen to anyone in that industry. Right. Just listen to me, and I've changed it. Which is kind of a nice segue to our next episode, where we'll tell you why the medical industry is entirely wrong, and we'll help you cure your cancer with essential oils. So make sure you listen to the next episode. It's going to be big.
Big flashing sign. We're not actually doing that. we are not going to be sponsored by a bunch of dietary supplements.
This was awesome. Thanks so much, Carl.
Thanks. See you next week.
Bye.